Greetings. Today let's talk about the conservation of momentum. We're going to talk about what conservation of momentum is, the principles behind it, and we're going to apply it to different types of collisions using the conservation of momentum here. So, what is conservation of momentum? Well, physicists have found that there are certain things in the universe that you just can't violate. One of those things is the law of conservation of momentum. There's only so much momentum in the universe, and there's never going to be any less or any more. You've probably heard of things like the conservation of energy or conservation of mass. Well, honestly, momentum is even more important to conserve than either of those. So the momentum in a system is always conserved. It can never be created or destroyed. So that's probably how you've heard about conservation before: never created or destroyed. It can just be transferred from one place to another. Now, specifically, kind of more mathematically, what we mean is the total momentum before is equal to the total momentum after. Now, before and after, we mean before and after something happens. So something changes the system to where this ball has some momentum, and then suddenly it has less or more momentum. Well, something else then has to gain that momentum. And that happens in collisions often. So where we often see momentum being transferred is through collisions. Now, mathematically, we can write this as a statement using P before equal to P after. So the total momentum before a collision has to equal the total momentum after a collision. Well, we know that momentum, P, is equal to mv. So I could just add up the mass times the velocity for all of these momenta before and after, and I have a mathematical expression that relates the conservation of momentum. So P before, let's say I have two objects, two balls that are flying at each other, and they're going to collide in the middle. What I can say is that the momentum before the collision, which would be the mass of ball 1 times the initial velocity of ball 1 plus the mass of ball 2 times the initial velocity of ball 2, that's going to be equal to the mass of ball 1 times the final velocity of ball 1 plus the mass of ball 2 times the final velocity of ball 2. So I get this big, long equation to relate these two momenta here. And this can be expanded to include any number of objects. Physicists have done this with tens of thousands of objects in one simulation. But we're only going to be considering collisions that have two objects in them. So we're going to keep it nice and simple here. Now, there are a lot of ways to look at momentum and conservation of momentum in a system. Two important distinctions when we talk about collisions are whether those collisions are elastic or inelastic. You might have heard of these before, in fact. An elastic collision is a collision that conserves kinetic energy. So besides just conserving momentum, an elastic collision, sorry, I'm going to say conserves and not conserving, conserves kinetic energy. So it conserves two things there. Now, you might have heard of these collisions before. They come up in chemistry a lot. If you took chemistry last year, you might remember that collisions between gas particles are elastic. And so that's a type of collision that conserves both momentum and kinetic energy. So gas particles colliding is that. But even if you just take a ball and you drop that ball on the table, if you look at where that ball is, let me make a little room here. If I drop that ball on the table, it's going to bounce back up. That kinetic energy that it has when it comes down comes back up, and I get that kinetic energy back out. So kinetic energy is conserved. That's different than a lot of other collisions that we see. Take a car crash, for example. If I take a car and I smack it into a tree, that momentum is conserved. That momentum transfers from the car into the tree, but the car is going to stop. So there's no kinetic energy anymore, and so there's no conservation of kinetic energy. So what an inelastic collision is an example of that is a car crash. What it is a collision that does not conserve kinetic energy. Now, let's take a look at the types of collisions that we're going to have to do mathematical calculations on. There are three broad types of collisions that we're going to see here. The first one is a type of elastic collision. What we're going to take a look at are elastic collisions that have two objects that bounce off each other. So bounces are what we're going to consider first. A type of inelastic collision that we're going to take a look at is a collision that happens when two objects come together and one sticks to the other. We actually call this a perfectly inelastic collision. Two objects come together, stick together, and keep moving forward. So we're going to say sticking objects here for our next collision. And then our final type of collision that we're going to see are collisions where two things actually start and explode apart. So start at rest and explode apart, we're going to call those explosions. So it's not a collision per se, but it can be solved the same way, where you have two objects flying apart from each other. Okay, let's take a look at some examples of how we're actually going to solve this here. Our first example says, I have a 0.5 kilogram red billiard ball moving at 2 meters per second to the right, and it strikes a stationary 1 kilogram blue billiard ball. After the collision, the red billiard ball is moving at 1 meter per second to the left. What's the final velocity of the blue billiard ball? Now, there are two ways that we can go ahead and solve conservation of momentum problems. I particularly prefer the first way, but I'll show you both the way you can use either one. The first way is using what I call a momentum table. We're going to list all of the objects and their momenta in a table, add them up for both the before and after the collision, and then solve to find the unknown variable. So to list out my objects that we have here, our known objects include the red billiard ball and the blue billiard ball. Our next column is going to have the initial momentum. And let's go ahead and put the units in here, kilogram meters per second. That way I don't have to keep putting units in my table. As long as I have units in my column headers, I'm good to go. So let's consider the initial momentum of the red billiard ball. It's moving at it has a mass of 0.5 kilograms, and it's moving at 2 meters per second to the right. Now let's go ahead, I've called this positive, so let's say that to the rightward direction is positive. Direction matters when it comes to momentum, because momentum is a vector quantity. So 0.5 times 2, that gives me 1, is my initial momentum of the red billiard ball. For the blue billiard ball, it's moving at 0 meters per second initially, and has a mass of 1 kilogram, so 1 times 0 is 0 for its initial momentum. So the total initial momentum, if I add these up, is 1 plus 0, which is 1 kilogram meter per second. So that's my initial momentum for the entire system. Let's go ahead and take a look then at our final momentum. P final, we're going to again measure that kilogram meters per second. For my red billiard ball, it says after the collision, same mass as 0.5 kilograms, but it's now moving 1 meter per second to the left. Since I made right positive, we're going to make that minus 1 meters per second. And then for my blue billiard ball, it has a mass of 1 kilogram, and I don't know its final velocity, so I'm going to call that VF. Well, here, same way I did before, I can add these up. 0.5 times minus 1 is minus 0.5, and then I have my VF as 1, so this is going to be VF minus 0.5. Again, the conservation of momentum tells me the momentum before has to equal the momentum after, so I can set these equal to each other. 1 equals VF minus 0.5, so VF is just equal to 1.5 meters per second. So that's how we'd solve this problem using a momentum table. The other way that you can solve these problems is by actually just using the conservation of momentum equation. So we'd have to write out that big equation. We know that the initial momentum, or the momentum before, is equal to the final momentum, the momentum after. That means that m1 vi1 plus m2 vi2 equals m1 vf1 plus m2 vf2. Now I have to plug in all my numbers here. Let me make sure I have the right numbers here on my sheet. So I start off with my red billiard ball as a mass of 0.5 kilograms, and it's moving at 2 meters per second to the right. We made that positive, so it's positive there. I'm going to add to that the 1 kilogram. Let me make a better 1 there. 1 kilogram for my blue billiard ball. It's stationary, so its velocity is 0 meters per second. That's going to equal, for my red billiard ball, 0.5 kilograms times VF, which was, I believe, negative 1 meters per second. It's moving to the left. I'm going to add to that the 0.5 kilograms, sorry, not 0.5, but 1 kilogram, times the mass of the blue, or times the velocity of the blue ball, which we don't know. So solving this all out, 0.5 times 2, this is 0. That ends up being 1 kilogram meters per second. That's going to equal minus 1, or sorry, minus 0.5 kilogram meters per second, plus 1 kilogram times VF. Solving that for VF, I get 1.5 divided by 1, or 1.5 meters per second. The same answer I saw before, this just time using the conservation of momentum equation. Okay, I have a lot of example problems that we can do here. What I'd suggest that you do is go ahead, solve them out here, and then come back, watch the rest of the video, and make sure that you can get the same answers that I do here. Okay, let's take a look at example 1. In example 1, I have a 1 kilogram cart moving at 10 meters per second along a frictionless track. It collides into a 2 kilogram cart at rest. The 1 kilogram cart stops, and the 2 kilogram starts to move. What is the velocity of the 2 kilogram cart? So, going ahead, listing out my objects here. I've got cart 1, and I have cart 2. Doing the initial momentum in kilogram meters per second, I know that cart 1 has a mass of 1 and is moving at a velocity of 10 meters per second, so that has an initial momentum of 10. We're going to go ahead and make the right direction positive, just so I know that we're going to keep that direction the same. For cart 2, it's at rest, so its initial momentum is 0. So my total initial momentum is 10. For my final column, cart 1 still has a mass of 1 kilogram. It's going to stop though, so its final momentum is 0. For cart 2, I know it has a mass of 2 kilograms, but I don't know its final velocity, so adding these together, I get 0 plus 2 VF. These two sides of the equation have to be equal to each other. The initial momentum of 10 has to equal the final momentum, which is just 2 times VF. Solving that out, VF must be equal to 10 meters per second. Okay, let's take a look at example 2 here. In example 2, I have a 0.015 kilogram toy car moving to the right at 0.02 meters per second and has a head-on collision with a 0.020 kilogram toy car moving in the opposite direction at 0.030 meters per second. So we've got my two toy cars here. We're going to call them car 1 and we're going to call it car 2. Now for the initial momentum of both of my cars here. For car 1, it is 0.15, don't forget that 0 there, times 0.020, and that's going to go ahead to the right, and we're going to make the right direction positive. Then for car 2, my car 2 is moving in the opposite direction and has a mass of 0.02. So we're going to say 0.02 times the opposite direction, negative 0.03. Got to make that negative because it's moving to the left. That's its initial momentum. For the final momenta here, for car 1, after colliding, it's moving with 0.37 to the left. We made right positive. So for car 1, it is now switched, same mass, but its velocity is now negative 0.37 meters per second. I do not know the velocity of car 2 after the collision, so that's going to be 0.02 times VF. So go ahead and adding these up here. 0.015 times 0.02 is 3 times 10 to the minus 4th. 0.02 times negative 0.03 looks like that's negative 6 times 10 to the minus 4th. So I, in total for my initial momentum, get negative 3 times 10 to the minus 4th. That just means that the momentum initially is more to the left. That's going to be equal then to my final momentum. 0.015 minus 0.37 is going to end up being negative 5.55 times 10 to the minus 3rd. And that's going to be added to 0.02 VF. Those are set equal to each other because the initial and final momentum are equal. Setting that and solving for VF, I end up getting a VF of 2.63 times 10 to the minus 1st meters per second, or just 0.263. Okay, let's go ahead and try example problem number 3. Now, those first two examples were examples of those elastic collisions, those bounces here. But now we're going to go ahead and take a look at some inelastic collisions, collisions where two things stick together. So, problem number 3 says, your 80 kilogram friend is so happy to see you again and is running for you with a speed of 5 meters per second. You are stationary and have a mass of 90 kilograms. On impact, you're swept off your feet and find the two of you are moving together. Calculate the speed you and your friend are moving at. So to solve this one out here, we've got you and we've got the friend. Now we could use a momentum table, but I want to go ahead and show you how you'd solve this just using the conservation of momentum equation. So if you did a momentum table, that's perfectly fine. See if you get the same answer that we did here. So my conservation of momentum equation says that m1 vi1 plus m2 vi2 equals m1 vf1 plus m2 vf2. Plugging in my numbers here, we've got the 80 kilogram friend times your initial speed of that friend, which is 5 meters per second, plus your mass of 90 kilograms, times your speed, which is 0 to start off with. That's going to equal 80 kilograms times your friend's final speed, and then plus 90 kilograms times your final speed. Now, because you stick together, these two are the same. And so on this side, this just reduces down to 170 kilograms times VF. That 0, 80 times 5, ends up being, it looks like, 400 kilogram meters per second. So solving that out, 400 divided by 170, for my final speed, I end up getting 2.35 meters per second. Okay, let's go ahead and take a look at problem number 4 here. Problem number 4, very similar, has you with a different mass and a different massed friend. So we have a 75 kilogram friend. Let's go ahead and put down our equation first though. M1 V1I plus M2 V2I equals M1 VFI, or VF1 plus M2 VF2. We now have a 75 kilogram friend, now moving at 6 meters per second. We're going to add to that your momentum, which is just 0. That's going to equal to your two masses added together. So 75 kilograms plus 85 kilograms times that final velocity, VF. Solving this out here, 6 times 75. Looks like that ends up being 450 kilogram meters per second. And we're going to set that equal to 75 plus 85, which is 160 kilograms, times VF. Solving that out, VF, it looks like, is 2.81 meters per second. Okay, 2 more to go here. Let's go ahead and take a look at one last type of collision, this time explosions. Here, we have a student who's standing in the middle of a frictionless pond having a radius of 5 meters. He's unable to get to the other side because of the lack of friction between his shoes and the ice. To overcome this difficulty, he throws a physics textbook horizontally toward the north shore at a speed of 5 meters per second. How long does it take him to reach the south shore? So you've got a student initially standing there with his textbook. Now, when you think about our momentum table, our two objects are the student and the textbook. Before anything happens, what are the momentum of each of those? Well, before he throws the textbook, the momentum of the student is 0, and the momentum of the textbook is 0. So my total momentum ends up just being 0 initially. Then for my final momentum, after you throw the textbook, we know that the textbook is now moving to the north shore. So let's make north positive. We know moving toward the north shore at 5 meters per second. So its momentum is 2.6 times 5. Now your momentum, you know your mass. Your mass is going to be 730 divided by 9.81, which it looks like I calculated out to be 74, roughly, kilograms. You don't know your final speed, so that's VF. So add these up here. 5 times 2.6, which is 13, is going to be that, plus 74 VF. That's going to be equal to 0. When you solve this for VF, you're going to notice that ends up, it looks like, being negative 0.18 meters per second. Why is the negative there? Well, because you're going to be moving the opposite direction. If you move the textbook north, you end up moving south, so the negative makes sense. And to figure out how long it takes you to reach the shore, all you have to do there is, because we're assuming it's a frictionless surface here, V is equal to d divided by t. You know that your velocity is negative 0.18 meters per second. You're going to be going 5 meters. Let's just ignore the negative here because we don't want a negative time. Our time, it looks like, ends up being 28 seconds. Okay, problem number 6 here. We've got another 730 Newton unnamed physics student now launched from a 500 kilogram cannon. I'm sure we could all guess exactly what student this is going to be. So we've got our student sticking out of our cannon here, and we're going to fire them toward that wall right over there. Now again, the initial momentum for both the cannon and the student end up being 0. So when you list out your variables here, your initial momentum, pi, in kilogram meters per second, ends up being 0 and 0 for a total momentum of 0. Now, let's consider the final momentum. We know exactly what happens to the cannon. The cannon recoils. It's moving backward at the speed of 1.2 meters per second. Let's go ahead and say that the forward direction is going to be positive. So for my cannon, it's going to be moving. It says a 500 kilogram cannon at negative 1.2 meters per second. The student then has a weight of 730, so the mass is 74 kilograms. We don't know our final velocity. Now, setting this up here, it looks like I have 74 VF minus 600, just from the minus sign there. That means that equals 0. So 74 VF equals 600. My final velocity should be 8 meters per second. It's positive because the cannon was moving backward. You could have set it up another way. You would just get a negative answer there. Okay, that's been conservation of momentum. Hope this has helped you. If you have any questions, just let me know. Thanks. Okay, back up. Okay, we're almost done with me talking.
Uh-oh.
But I guess I
This
have enough
Mac
to do.
can't connect to the iCloud.
Okay. Cool. I'm gonna talk about these collisions. Now let's look at. Now I'd like to look at. It's hard getting like in.
Now I'd like to look at.
Yeah, I know.
Okay.
You're in the video just slightly in case you didn't know. Now let's like the.
You should put all of those.
So
more
much,
like a
it
class.
feels more like a class. And so then I have that computer recording that.
Wait,
and
it's
then
recording currently.
It is currently recording, yes. And then this one records the actual screen movements on the screen here. That's how that works. This is
So like,
got audio working.
so like, if I just popped up in the middle of this, you could see me.
We already see.
We already
see your
saw
head.
your head.
You can't
Just
see me
pop up
now
in
though.
there. So I could be like, and to help us out for my first example problem, we have Mr. Justin Moranti coming in to help us out.
Yes.
Okay. So, we have a 1 kilogram car. Oh. Oof. You just